It was a holy moment. The Andromeda Nebula overnight became the Andromeda Galaxy.
The James Webb telescope has identified 6 galaxies that exist 500 million years after the Big Bang. This is incredible. When you look at the night sky, you have a pinpoint of light. A pinpoint of light in the night sky expanded gives you one of these pictures from the Webb Space Telescope.
Even the most seasoned scientists are stunned by the latest image from the James Webb Space Telescope, which has elevated space exploration to new heights. The famous physicist Michio Kaku has now spoken out about this astounding discovery. Observe how many galaxies there are in these pictures, with each galaxy having 100 billion stars. There's no denying that they're most likely out there. Referring to it as a true gamecher in terms of our cosmic knowledge, there's a problem. Our theory of the universe's creation might need to be revised. This picture might completely alter our understanding of the origins and development of the cosmos. What has Webb discovered, and why is Kaku referring to it as the most important discovery of our time? The final fate of the sun and our interest in stars. For thousands of years, people have been enthralled by the sun, our nearest star. Numerous cultures have studied, worshipped, and worked with it since it gives the warmth and light that enable life on Earth. The intricate process of nuclear fusion determines the sun's life cycle, despite its constant presence in our everyday lives. In the sun's core, hydrogen atoms combine to form helium during this cycle, unleashing enormous amounts of energy. The sun will progressively change over billions of years, going through several stages such as the main sequence phase, a red giant phase, and ultimately a final phase where it sheds its outer layers. According to astronomers, the sun will enlarge so much when it reaches its red giant stage that it might swallow up the inner planets, such as Mercury and Venus, and fundamentally change the ecology on Earth. It will leave behind a core called a white dwarf, as its outer layers are expelled into space. In order to demonstrate that even things as magnificent and seemingly eternal as stars may not last forever, this little, dense, stellar remnant will gradually cool over time. We are reminded of how ephemeral and active cosmic structures may be by the fact that every star in our galaxy, and indeed the entire universe, follows a course determined by these processes of birth, evolution, and final death. We knew very little about how stars worked for a large portion of human history. Early astronomers only identified constellations, patterns of luminous points in the sky. As telescopes improved throughout the centuries, they were able to see stars as flaming spheres of helium and hydrogen. A major turning point was realizing that our sun is one of billions in the Milky Way. Astronomers soon found innumerable galaxies outside of our own. This broadened our understanding of the cosmos and sparked other inquiries into cosmic evolution, star births, and star deaths. In order to comprehend how the sun affects planetary atmospheres, scientific missions subsequently concentrated on studying the sun's magnetic fields and corona. Understanding how life can arise near other stars and safeguarding satellites from solar flares depend on this kind of research. Even while the sun's future appears far off, it is still very much a part of our own, which motivates researchers to continue studying its workings by monitoring solar winds and sunspots. By better understanding space weather, scientists have been able to safeguard vital earthly networks and electrical systems. Early galaxy observations and the requirement for sophisticated telescopes. Even with early telescopes, people could only see a scattering of stars when they looked up at the night sky before powerful telescopes were constructed. In addition to studying individual stars, astronomers also observed fuzzy areas, frequently referred to as nebulae. The fact that these patches were actually whole galaxies with billions of stars was not immediately apparent. The major breakthrough occurred in the early 1900s when astronomer Edwin Hubble demonstrated that certain nebulae were located outside the Milky Way's boundaries using data from the Mount Wilson Observatory. His research changed our perception of the universe forever by proving that our galaxy was just one of many. More advanced telescopes that can gather light at different wavelengths, such as visible, ultraviolet, and infrared bands, were developed as a result of this discovery. When scientists discovered that galaxies may be irregular, elliptical, spiral, or any other shape, they knew that more precise data was needed to track the formation, evolution, and occasionally collisions of these massive star systems. These cosmic subtleties would be obscured from view without sophisticated technology, which would restrict our understanding of the complete intricacy of the world. As we found gas clouds and star clusters creating new star generations, as well as black holes and galactic centers, our interest grew. Astronomers started tracing the structures of galaxies and determining their distances using techniques like Cepheid variable stars as telescopes got better. By examining galaxy rotation and the rate of space expansion, these techniques allowed us to uncover secrets and find dark matter, giving us a more realistic sense of the universe's vastness. In light of these inquiries, scientists became aware of the limits of ground-based telescopes, such as interference from the Earth's atmosphere. They also had to deal with urban light pollution. We now have space observatories like the Hubble Space Telescope because to this endeavor to put telescopes into orbit, Hubble transformed the study of the cosmos by capturing clearer images at invisible and ultraviolet wavelengths while avoiding atmospheric distortion. In order to detect feeble infrared signals from faraway galaxies generated soon after the Big Bang, astronomers subsequently started looking for even more penetrating devices. The expanding cosmos frequently caused these signals to shift to longer wavelengths, which is why infrared detection is so important. Finding hints about how matter initially arranged itself into stars, star clusters, and galaxies with intricate structures was one of the promises of studying these old galaxies. Engineers and researchers worked together worldwide to create increasingly sophisticated space systems motivated by a need for precision. The Space Telescope of James Webb. The urge to explore the universe more thoroughly than ever before led to the creation of the James Webb Space Telescope, also known as JWST or Webb. In order to create an observatory that could see deeper in infrared wavelengths than its predecessors, engineers, scientists, and space agencies collaborated. In collaboration with the European Space Agency and the Canadian Space Agency, NASA spearheaded this enormous project. A common dedication to expanding the frontiers of cosmic discovery was reflected in the influx of funding and technical assistance from numerous nations. Although its capabilities would reach into an area of the electromagnetic spectrum that Hubble had not yet thoroughly examined, the telescope was intended to be a successor to the Hubble Space Telescope. Teams meticulously examined which sensors could best capture far-off starlight that had traveled for billions of years across an expanding universe as planning got underway in the 1990s. Large engineering challenges have to be overcome during the Webb's design phase. The telescope would be in the infrared, thus it needed to stay very cold so that its heat wouldn't overpower the weak signals it was looking for. To hide Webb's mirrors and equipment from the sun, planners created a special sun shield the size of a tennis court that is made up of several reflecting layers. This massive sun shield in the telescope's segmented primary mirror had to be folded by the designers in order to fit onto a launch rocket. After entering space, Webb would have to go through a difficult unfolding phase that would require hundreds of single-point failures in order to succeed. Every component has to work perfectly, or the mission as a whole may be jeopardized. In order to replicate the chilly vacuum of space and the tremors of launch, this high-stakes design required extensive testing on Earth. The instruments themselves demonstrated the global scope of the Webb, with the Fine Guidance Sensor FGS being the result of several agencies contributing their own areas of expertise. The James Webb Space Telescope successfully launched on an Ariane 5 rocket from French Guiana in December 2021, following years of delays and financial worries. Positioned near the second Elaine point, approximately 1.5 million kilometers from Earth. The orbit in which Webb travels was selected to maintain stability and consistent alignment with the Sun and Earth. With the goal of unlocking basic mysteries regarding the cosmic past, galaxy formation, and the physics underlying planetary systems throughout the universe, it can observe far-off objects without interruption from this vantage point. Vision infrared. The capacity of Webb to detect infrared light is one of its primary selling advantages. This capability is essential for looking through cosmic dust and observing objects that are very far away. Redshift is the term used to describe the movement of light from far-off galaxies toward the red end of the spectrum as the universe expands. This light might have extended into the infrared spectrum by the time it reaches us. This extended signal is difficult for conventional optical telescopes to detect, but JWST's equipment are excellent at doing so. This benefit enables scientists to examine galaxies that formed during the cosmic dawn, which occurred just a few 100 million years after the Big Bang. Scientists can piece together how quickly galaxies evolved, how stars formed in those galaxies, and what kinds of chemical elements contributed to that early growth by gathering evidence across a variety of infrared wavelengths. Studying dusty regions where stars are formed is another benefit of infrared observation. Through a standard telescope, regions such as the Carina Nebula look as bright, fuzzy patches. However, the creation of young stars and planetary systems may be obscured by the dust there. What lies beyond those clouds is revealed by infrared coverage, which advances our knowledge of how planets form from whirling disks, how stars accumulate mass, and how various gas pockets may collapse due to gravity. Furthermore, by employing infrared techniques, objects in our solar system, like Titan, Saturn's largest moon, can be thoroughly examined to reveal features like ice formations and methane lakes that may not be evident in photographs taken with visible light. Astronomers can now see more detail than ever before thanks to Webb's advancements. More light is captured by its big segmented mirror, and highly accurate measurements of weak signals are made by its advanced detectors. This makes it possible to obtain high-resolution pictures that show complex features in galaxies, including as star-forming areas, spiral arms, and core bulges that may contain super-large black holes. Galaxies of different sizes and forms, some of which seem as tiny red dots, fill the frame in many deep-field images taken from the Webb. Our understanding of early star formation may be altered by these weak patches, which are frequently the oldest galaxies we have ever seen. Researchers can determine how rapidly these old galaxies formed their stars and whether or not their rapid development fits the present paradigm by examining infrared data. Older ideas that predicted youthful tiny galaxies at such early epochs in cosmic history are challenged by the fact that these galaxies sometimes appear more mature than anticipated. Problems with current models. Astronomers spotted an oddity in the data shortly after the Webb started providing scientific photographs. Instead of simply having the youthful blue stars that were predicted to predominate in the early universe, some very distant galaxies were found to be shockingly big and full of older red stars. According to conventional ideas, early galaxies that developed just a few 100 million years after the Big Bang should be small, chaotic, and primarily composed of hot, short-lived stars. But according to Webb's findings, there were redder, more developed stars and galaxies that seemed to be fairly mature. This discovery suggested that these galaxies had undergone more extensive or prolonged star formation processes, accumulating massive stellar masses quickly. In one study, red dots in deep-field photographs were investigated and discovered to correlate to galaxies that were significantly more star-rich than previously thought. Their existence 500 to 700 million years after the Big Bang forced scientists to reevaluate their theories. Some suggested that stars might have formed at an explosive rate due to early cosmic conditions. Others contended that star aging may have been accelerated by exotic processes, such as an unusual ratio of helium to heavier components. These possibilities, however, start to cast doubt on the conventional models of cosmic development, which typically assume a more gradual accumulation of galaxies over time. The puzzle may call for a more nuanced understanding of how matter coalesced in the early universe, or it may indicate new physics. The confirmation of these identifications requires spectroscopic follow-up. Certain chemical fingerprints can be seen by astronomers by separating the incoming light into its different wavelengths. They can determine if dust effects are distorting the hues, or if some galaxies are actually teeming with old stars. The speed at which galaxies can expand must be seriously re-examined if these results are correct. The discovery of large red galaxies during the first billion years of the cosmos raises the possibility that star formation processes are occasionally more severe than previously thought. On the other hand, these discoveries might indicate that cosmic expansion influences our measurements in ways that are not entirely explained, albeit that appears less likely in light of current cosmological evidence. In any case, the discovery of ostensibly ancient systems at such an early stage of cosmic history emphasizes the significance of Webb sensitivity and the enormous potential for new discoveries in previously poorly understood areas of the cosmos. Strange interactions between galaxies. The Webb has revealed spectacular events such as those in Stephan's quintet by focusing on current galaxy interactions in addition to the early universe. NGC 7318b, a cosmic intruder, is one of the 5 galaxies in this group. It travels at tremendous speeds through the space between its neighbors, creating shock waves through the surrounding thin plasma. Typically, supersonic velocity across a material is associated with shock waves. Additionally, in astronomy, they have the ability to heat or compress the gas they come into contact with, causing intricate reactions. These shock waves cause unexpected changes in molecular hydrogen, a key component of star formation, according to data from the Webb and the Potent Atacama Large Millimeter-Submillimeter Array. Scientists found that NGC 7318b produces massive arcs of turbulence where warm and cool gas phases coexist as it passes through the group. Theoretically, shock waves traveling hundreds of kilometers per second should destroy delicate molecules. Rather, it seems that the wavefront breaks up clouds into smaller clusters or cloudlets, which might potentially recycle hydrogen between warmer and colder temperatures. Researchers can map the movement and changes of gas by using warm molecular hydrogen as a tracer for these dramatic events. Although the specifics are still being investigated, such recycling might promote more star formation in areas that are able to cool down once more. Webb's results are even more intriguing, since they suggest structures that resemble gas bridges or tails, which may be dwarf galaxies or dispersed blobs of matter being dragged apart. These occurrences demonstrate how galaxy collisions may be both creative and destructive, causing starbursts and dispersing ingredients that become stars. Astrophysicists are amazed at how one rogue galaxy may trigger a series of events that drastically alter the surrounding environment, impacting the distributions of stars, gas, and even dark matter. To verify how fast the shock wave travels and how it affects the area as a whole, scientists plan to collect spectroscopic data to assess the temperatures and speeds of various gas layers. These observations go beyond Stephan's quintet. The bulk of massive galaxies most likely evolved through mergers, and many galaxies in the universe have experienced close encounters. By examining the shock waves and gas recycling in a single, well-observed instance, we can better comprehend these gigantic interactions and get insight into larger concepts of cosmic evolution and star formation that go beyond Stephan's quintet. Webb's remarkable sensitivity has produced advances in a variety of astronomical fields. A direct glimpse of a chaotic galaxy collision was provided by Stephan's quintet, but other targets have also shown unexpected things. For example, the telescope directed its infrared gaze toward the star-forming region of the Carina Nebula, revealing dust-covered young stars. Webb's instruments allowed astronomers to examine how these young stars take in mass from their surroundings for the first time by separating hot gas from cooler dust clouds. Views of the Southern Ring Nebula, which showed streams of material pushed out by a dying star, highlighted the chaotic aspect of stellar death. In each instance, Webb's data provided structural information that had been overlooked by earlier observatories. A significant boost was also given to planetary studies. Webb can find signs of carbon dioxide, water vapor, and other molecules by looking into the atmospheres of exoplanets. The telescope's spectroscopic capabilities are a gamecher for figuring out the makeup of other worlds, even though it isn't primarily an exoplanet hunter. In an effort to learn more about how planetary systems evolve and whether specific atmospheric conditions may indicate habitability, researchers have focused on gas giants that circle far-off stars. Although it is still impossible to directly detect life, these data help us determine which planets need more investigation. Nearer to home, the Webb has brought mysteries in our solar system to light. Jupiter was observed in greater detail than ever, revealing its faint rings and tumultuous atmosphere. Webb's infrared spectrum was able to penetrate Titan, Saturn's moon, through its thick, hazy atmosphere, proving the existence of methane seas and possibly exposing clouds of hydrocarbon compounds. These discoveries are crucial for understanding the chemistry that could support life in harsh environments and for organizing future trips to Titan. Astronomers are still pushing the boundaries of Webb technology by aiming it at unexpected objects. Unexpected vacant sky fields can occasionally display cosmic structures we never imagined existed or hidden galaxies that surpass predictions. Additionally, Webb can rapidly gather dim light due to its larger primary mirror than Hubble, which enables faster exposure times while still producing rich photos. Our sensation of awe is widened by each new discovery, which affirms that the universe is more intricate and varied than our models have thus far permitted. This encourages researchers to continuously revise their hypotheses, guaranteeing that astronomy will always be a dynamic science driven by fresh evidence. Technical features of Webb's tools and next research. Webb's collection of specialized tools is the reason for its remarkable science return. The most talked about camera is the NIAM near-infrared camera, which uses near-infrared wavelengths to create eye-catching images. This makes it possible to map the features within closer targets and obtain deep-field images that show extraordinarily distant galaxies. Another essential instrument for separating incoming infrared light into its constituent wavelengths is the near-infrared spectrograph, or NISP. This allows NARPEC to examine the atoms or molecules present in the source, ranging from heavier elements like carbon or oxygen to hydrogen and helium. Through Doppler shifts in the spectral lines, scientists may also measure the velocity of gas and stars, creating a dynamic image of how gas flows around young stars or how galaxies rotate. By exploring the mid-infrared region, where cooler objects radiate more intensely, the mid-infrared device MIRI expands Webb's wavelength coverage even further. It has been useful in the study of weak comets, dust clouds, and other objects that are harder to see at shorter wavelengths. Astronomers can create a multi-layered picture of star-forming areas, thick dust lanes, and galaxy-wide phenomena by integrating data from NIRCam, NESPEC, and MIRI. Accurate aiming and stability, which are essential for taking crisp pictures, are guaranteed by the Fine Guidance Sensor (FGS). Webb's ability to solve the early universe's conundrum is a result of this combination of tools: planetary atmospheres, star creation, and other topics. Scientists are excited to launch further in-depth spectroscopic campaigns in the future. They seek to evaluate the impact of black holes at galactic centers on star formation or verify the chemical composition of the first galaxies. In order to discover faint galaxies that might not be noticeable in smaller surveys or to catch unusual phenomena like supernovas in their prime, several groups organize wide-field surveys to randomly sample different regions of the sky. By gathering vast amounts of data, astronomers hope to improve or disprove theories on the formation of stars, whether some elements appeared sooner than anticipated, and the arrangement of the cosmic web of galaxies. Webb's results will be complemented in tandem by ground-based observatories that are outfitted with next-generation gear. Earth-based radio arrays can search for signals such as the distribution of cool atomic hydrogen that fill in the gaps in infrared data. Moving forward, multi-wavelength synergy is the strategy. To create a comprehensive picture of events, combine observations from many angles. Every single observation raises new issues, ensuring that future plans will advance the telescope's capabilities even further. Consequences for scientific research and cosmology. Webb's discoveries have already challenged certain long-held cosmological models and changed our understanding of how quickly stars and galaxies can originate. We need to consider how stuff clusters together under gravity and how rapidly nuclear fusion ramps up in stellar cause if enormous galaxies were there just a few 100 million years after the Big Bang. Furthermore, surprising findings like older, redder stars appearing in early epochs raise questions among scientists about whether we have undervalued things like the efficiency of star formation in extremely dense environments or the impact of dark matter halos. The field advances as a result of these discussions, which improve theory observation alignment and result in updated simulations. How heavier elements than hydrogen and helium emerged very fast after the Big Bang is one important question. Forging these heavier elements is typically explained by stellar nucleoenthesis in big stars and subsequent material recycling through supernova explosions. However, the rapid accumulation of metals may be explained if early stars were creating and dying in vast numbers. On the other hand, there might be novel, poorly understood processes, possibly involving exotic physics at work that enable matter to achieve higher densities or generate components more quickly. In order to probe metallicities and validate or disprove such theories, Webb's capacity to record spectra from faint old galaxies is essential. The fine-tuning of the universe's expansion rate is another field that Webb's discoveries have sparked. The Hubble constant, as it is known. New data confirm the existing tension between local observations and cosmic microwave background estimates, or offer new hints that resolve it even if previous telescopes help measure expansion more precisely. Webb's research could help determine whether the cosmic timescale is accurate or whether new physics, such a different kind of dark energy, is needed if it reveals systematic trends in galaxy brightness or star formation histories. In the meanwhile, the prospect of finding biosignatures on exoplanets continues to fascinate both the general public and the scientific community. Even though they are still in their early stages, Webb searches set the stage for future initiatives aimed at searching stony planets for chemical signs of life. Even if we haven't found conclusive evidence yet, any small step forward in spectroscopic resolution brings us one step closer to addressing one of the most ancient problems in human history. If there is life in the huge cosmic ocean somewhere else, pursuing the pursuit of greater understanding of the cosmos. Astronomers are extending their plans to explore areas of the sky that were previously thought to be too faint or remote for significant study, thanks to data from the James Webb Space Telescope. Numerous deep field initiatives are currently under progress, focusing on particular sky windows to collect light from a vast number of galaxies at various times. Researchers hope to create a multidimensional atlas of galaxy evolution by combining these observations with radio, optical, and X-ray data. Every surprising finding refines our understanding of how cosmic structures form, from the primordial star clusters that formed a few 100 million years after the Big Bang to the mature ellipticals and spirals we observe far later. Webb's accomplishments also serve as an inspiration to engineers on Earth. In order to work at even lower temperatures or to record a wider range of the electromagnetic spectrum, they are investigating methods to construct larger, more sophisticated instruments. The proposed missions might be enormous segmented mirrors that dwarf Webb's or fleets of small satellites that cooperate. Multi-agency collaborations facilitate innovation and share expenses as space agencies recognize. Thus, more international cooperation is in the works. The field gains from a communal knowledge base by pooling resources and experience, preventing advancement from stalling following the successes of a single mission. The success of Webb has also boosted educational initiatives aimed at igniting future generations' interest in engineering and astrophysics. Students are inspired to study physics, math, and programming by the exciting press releases they see about star-forming regions that are revealed in vibrant color. Astronomy is kept alive by this cycle of inquiry and discovery that is transmitted through new telescopes and fresh perspectives. In order to make difficult subjects approachable, Educators and outreach professionals use the visuals on the web to illustrate ideas like spectroscopy, cosmic scales, and the life cycle of stars. Beyond the next 10 years, Webb's research will continue to influence future space exploration projects. Future infrared probes may provide a closer look at Neptune's moon Triton, Jupiter's ice moons, and perhaps dwarf planets, from more accurate exoplanet imaging to missions to characterize the habitability of distant moons in our solar system. Interest in discovering the secrets of the cosmos increases with every new discovery that is made public. In this way, every time we uncover a new layer of the cosmos, the James Webb Space Telescope's moonshot status, extensive engineering achievements, and expensive costs seem justified. Thank you for watching the video. Please like and subscribe for similar content.